And we're going to begin with 2.1, question number 7. Okay, and question number 7 I just put on here so you would get used to working with variables. I give you 2 ordered pairs again, and I want you to find the midpoint. So we've got c, comma y, and we've got minus 5c, comma 7y. And what we want to do is we want to find our midpoint. Okay, so the first thing we're going to do is we're going to label our ordered pairs, x1, y1, and x2, y2. And that's a C there, not an A. Make sure it looks like a C. Okay, that's a C there. Now, we've got them labeled, x1, y1, x2, y2. I always like to write up the formula. That way we have it. The more times you write down the formula, the easier it becomes to just remember it and have it already there. And your midpoint formula is x1 plus x2 over 2 and y1 plus y2 over 2. Now it's going to behave exactly the same with variables as it would with numbers. It's really no different. Okay, we're going to combine like terms, and we're going to see what our midpoint is going to come out to be. So let's go ahead and plug our numbers in. So if I plug my numbers in, x1, which is c, minus 5c, because that's x2, over 2. And then we've got y plus 7y over 2. Well, that's easy enough to work with. C minus 5c, that's a minus 4c over 2. And y plus 7y, that's an 8y over 2. And that reduces down to a minus 2c and a 4y there. And that is all that I wanted you to do. Does it make sense what I want you to do? Just plug the variables in. Variables behave exactly the same as the numbers do. If I would have gave you this as a distance problem, it would have been much more difficult. So I was very careful and made sure that I picked the one that had the midpoint and not the distance. If you would have had to do the distance, you would have had to square and keep track of variables. Midpoint's much, much easier. Okay. Anything else out of 2.1 to look at? Are there any other questions out of 2.1? Anything else? Okay. And again, I think you'll find 2.1, if you haven't already worked on the homework, I think you'll find 2.1 to be pretty easy to work through. Not a lot of difficult concepts. 2.2, we've got question 10. Are there any others out of 2.2 to look at besides question number 10? Do we have anything else? Okay, well, if not, then we'll do question 10, and we can always add more to the list. So let's look now at 2.2, question number 10. And so what we want to determine is if this is a circle or not, and if it's not, then we want to go ahead and say what it is. Now I'm going to make my life a little bit easier, and I'm going to move that 90 over. We could write it and move it over again. I don't really want to have to write it multiple times, so I just move the 90 over. Now, what makes something a circle? When we get it in center radius form at the very end, this number had better be positive, right? If it's negative, it's non-existent at the end. If it's 0, that means it's not a circle and it's simply a point, which is your center. But we don't know that until the very end. Now, we're going to go ahead and complete the square. So let's look at the x part. And for the x part, we've got x squared plus our 6x. Okay, so what's our procedure? Well, what we do, remember, is we half and square. So that's what we always do, is half and then square. So what's half of 6 now? 3. And 3 squared is a 9. And we always have to keep track of whatever we add on. Now we repeat the process with the y part. And that's y squared minus 18y. So half of a negative 18 is a negative 9, right? Half square. And then what are we going to have to add on now? What's going to go here? Can someone tell me? What's going to go in the blank here? That's going to be 9 what? Squared, which is 81. Just to make sure we're on the right track here. So there's your 81. Okay, now we put everything back together. Now don't forget about this negative 90 here. So let's rewrite it. And we've got x plus 3 quantity squared plus y minus 9 quantity squared equals, we still have our negative 90 from up here. We're going to have to add to that 9 and add to that 81. So now that then makes the right-hand side equal 0, doesn't it? And if it's equaling 0, what do we know? Is this a circle anymore? No, it is not a circle. What is this? Okay, it's going to be the point. And what's the point? The center. So it is the point. We switch our signs, remember. Minus 3, positive 9. It's not a circle because that. If it would have been a negative 3, then it would not be a circle and the graph would be non-existent. If it would have been a positive 4, it would be a circle with a radius of 2. Right? So if it's equaling 0, it's not a circle. And what is it? It's a point. If it's a negative, it's non-existent. And if it's equaling a positive number, it has a center and it has a radius. Are there any other questions out of 2.2 to look at? Anything else? Okay, well, let's then go ahead and now talk about 2.3, which is functions. So we're going to go ahead and begin talking in 2.3 about functions. Now, when we talk about functions, a function, what it is it's a way of changing things. Okay, something goes in and something else comes out. And a classic example of that is going to be, let's say, a gas pump. When I go to the gas station, this is an example of a function, and a gas pump is an example of a function. Because when you go to the gas station, you put money in, and what do you get out? Gallons of gas. This is an example of a function. Something goes in, something else goes out. Comes out. Okay, it changes it. Now, normally in mathematics, we use numbers, and this would be your x going in, and your y comes out. But this is an analogy of what a function is. Something goes in this case, money. Something else comes out. Lots of different examples. Another example is your salary. Okay? Hours worked goes in, paycheck comes out, right? Something goes in, it changes and gives you something else out. So this is an example of a function. So this one is a function. This one is not going to be a function. We can go back to the gas pump again. So let's say we put $5 in, and we get out, let's say, 1.5 gallons of gas, and we get out 4 gallons of gas. Does this make sense at all? No, why not? Okay, if I put $5 in, I better get out the same amount of gas every time, right? If I go to the gas station and I give if I put $5 on my credit card at the gas pump, I'm going to get out 1.5 gallons. Not 1.5 gallons, or the next person gets 4 gallons, right? That makes it not a function. This is not a function. And why is it not a function? Because one input cannot be split up to several outputs. It doesn't make sense, right? Gas has a fixed price. If I go to the gas station, it's $3.50 a gallon, right? That's what it runs. Might be a little cheaper, might be a little more. But if I put $5 in, I get out 1.5 gallons of gas. The next person had better get the same amount out, right? If they get 4 gallons out, there's a mistake with the gasoline pump. So this is an example of something that is not a function, because one input cannot be separated to several outputs. Now, you can have something where they all go to one number out, and that's okay. Here's another example. This one's going to be a function, and we're going to talk about why this one is a function. So here's an example of a function again. Okay, so let's say we work 10 hours at $10 an hour. How much would I get out? Okay, 10 hours, $10 an hour, I would get out and I would get paid $100, right? 10 hours of work, $10 an hour, I get paid $100. Well, what happens if another person comes over here and let's say they only work 5 hours, but they get paid $20 an hour? They still get the same what? $100 coming out, right? That makes sense, doesn't it? This is a function. Because each one, they map to the same $100, but this can happen. At every company, not everyone makes the same amount of money. Right? So this is an example of a function. I work 10 hours, $10 an hour, I get $100. Another person comes along, they only work 5 hours, but they make $20 an hour, so they also get what? $100. That's a function. It makes sense. Not this. Right? If I spend $5 on gas, I better get out 1.5 gallons. That's what it should be on the price. Not sometimes 1.5 gallons, other times 4 gallons. That does not make sense. Okay? Each input has to go to one unique output, because this is the in and this is the out. Now let's look at ordered pairs and see how they relate to functions. And we're also going to talk about domains and ranges. And the domain is what you get out, or sorry, what you put in. And the domain is usually going to be the values of x. And the range is the values of y. Sometimes the range is called the target. I'm now going to give you some ordered pairs, and we're going to tell if these ordered pairs are a function or not, and we're also going to find the domain and the range. So here's some ordered pairs. About 5, 3, 8, 2, 9, 1, and 3, 3. Okay, so these are our ordered pairs. Now, I think the easiest way to tell if this is a function or not is make a mapping. Okay, I like to make mapping so you can visually see what's happening. This is your x, and this is your y. So 5 maps to 3, 8 maps to 2, 9 maps to 1, 3 maps to 3. Is this a function? Yes or no? Okay. How do we know if it's a function? Well, if it is a function, each value of x should be different. They can all go to the same number, and that's okay, right? These can go to the same number. That's okay. As long as all the x's are different, that makes it a function. So this would be a function. And that's going to be a function since all the x values are different. Okay, so all the x values are different. That makes it a function. We can also get the domain and the range. Domain is going to be our values of x. So we're going to list out the values of x. We want to put them in the correct order. So I'm going to list them out from smallest to largest. And duplicate values, if we have any, we only write them once. In this case, all the x's are different. But if we had duplicate values, we would write them one time. So let's start with our domain, our values of x. So our smallest number is 3. We've got 5, 8, and 9. Now the range is the values of y. Duplicate values, we only write one time. And our range would be 1, 2, and 3. So this is a function. Okay, why is it a function? That's very easy to tell. All of your x values have to be different. So that tells me that this is a function. We listed out our domain and our range. Domain is the values of x. Range is the values of y. Some textbooks call the range the target. We use the word range, but other textbooks may use target. Let's try another one. Here's another set. How about 5, 4, 3, 8, 5, 2, 6, 1, and 7, 3. Same question. Function or not a function? Now, I think the easiest way to see this is visually draw them out. So use a mapping and see how they map together. So 5 maps to 3. Or sorry, 5 maps to 4. That's my mistake. 5 maps to 4. That's your x and your y. 3 maps to 8. 5 maps to 2. 6 maps to 1. And 7 maps to 3. Is this a function? Yes or no? Can anyone tell me if this is a function or not? Okay, no. Why is it not a function? It's not a function because you've got duplicated 5s, right? So this is not a function. It would be called a relation. Circles are relations. They're not functions. And we'll talk about those in a graph here shortly. So this is not a function. Okay, so let's go ahead and get our domain. And domain is the values of x. And we list them out from the smallest to the largest. So that's 3, 5, 6, and 7. And remember, domain goes with the x. Range goes with the y. And our range would be 1, 2, 3, 4, and 8. That should be all of them there. So do we see the difference between a function and not a function when I give you ordered pairs? What do you have to look for? If it's a function, very easy, all those x's have to be different. Okay? That makes it a function. It works. Because in mathematics, we want to make sure that we get the same answer every time. If I plug a 5 in and I evaluate a function out, I should get out 8 every time. Not 5, I plug it in today, I get 8. Next week, I get 12. It doesn't work like that. Mathematics has to be black and white. Something goes in, something else comes out. Not sometimes one thing comes out, sometimes something else comes out. Very black and white. Something goes in, something else comes out. And that's what a function does. It just changes things. Now we're going to look at graphs. And we're going to talk about these graphs and see if these graphs are functions or not. And we're going to use what's called the vertical line test. And many of you are probably already familiar with the vertical line test. And for the vertical line test, all we have to do, bless you, is you draw vertical lines. And if any line touches the graph at more than one place, it is not a function. So I'll give you a moment to get this copied down. Now, we do have a horizontal line test, which we'll talk about that later on. Towards the end of the course, when we talk about inverses, which is a whole different topic, we have a horizontal line test. And that's going to tell you if something's 1-to-1 or has an inverse. We will get to that later on, but in this chapter, we're talking about the vertical line test. We're talking about functions. So all we have to do is you draw vertical lines, and you see if any line touches that graph at more than one place. And if any vertical line touches the graph at more than one place, it is not a function. So very, very simple. So we're going to look at a few of these. We're going to see if these are functions or not. And then we're also going to get the domain and the range. So here's our graph. And let's say this is up here at 7. Okay, so that's going to be at 7. Now, is this graph a function? Yes or no? Let's see if this is a function. How do I know it's a function? Well, if it's a function and I draw vertical lines, each line is only going to touch the graph at one place. So each time I draw a vertical line, each line touches the graph at one place and one place only. So this would be a function. And now we talk about our domain. Here's negative x and here's positive x. And this is infinity and infinity. So this is positive infinity and also negative infinity. Remember, these are our x's. Now, what we're looking for is the domain. Okay? And the domain is the values of x. So, let's look at our graph here. Right? When I graph this, what's happening as I start here and as I go up? As I go up, I'm going to the left, and I'm also doing what? Going to the right. I'm going up to the left and up to the right. So that means I'm going for my domain from negative to positive infinity. Because you're going up, you're going left and right. Now, what about the range? The range is the up and down part. And here's positive infinity, here's negative infinity, and this is negative y, and this is positive y. Okay, so what's happening with this graph? Does this graph go down below here at all? No. Where does it start at? Looks like it starts at about 7, and what is it doing? It's going up. So my range would be, we use a square bracket, 7, and where does it go to? Infinity. And infinity always, no matter what, gets parentheses. Okay, so that's your domain, and that's your range. This section is very visual. We look at a lot of pictures. It's not a lot of calculations. It's more visual and understanding the graphs. So I'm going to give you another one to look at now. What about this graph? Function or not a function? Okay, it's a function. All lines are functions, unless it's a vertical line, but this one's going to be a diagonal. It's a function. What about my domain? Does anyone have any idea on what the domain would be? Does anyone remember from previous courses? If I gave you this line, what would your domain be? Let's think about what we do here. When we talk about the domain, what are we looking at? Okay, we're looking at the x values, left and right. So as this line goes up, what is it doing? It's going up, and it's also going over to the right. And as we go down, and we follow the graph, what is it doing? It's going down, and it's also going back where? To the left. So what would my domain be? Negative to positive infinity, because it's going down to the left, up to the right. What about my range? Does anyone know what the range would be? Can anyone tell me? Okay. Range is the values of y, so that's the up and down part. So what would that be? Does anyone have any idea? Same as the domain, and that's going to be negative to positive infinity, right? Because look at your graph here. You're going up through the ceiling. That's going up to positive infinity. The other one is going what? Down, and it's going down to negative infinity. So your domain and your range are both negative to positive infinity. Let's look at one more that is a function, and then we'll look at some that aren't. Okay, so here's another one. We've got a horizontal line. This one would also be a function, right? Because every vertical line crosses that graph at only one place. So this would be a function. What about the domain? Can anyone tell me what they think the domain would be? A domain is the values of x, not the y, the x values. The left and right part. Anyone want to take a guess as to what the domain would be? Very good work. Yep. Negative to positive infinity, because you're going to the left and you're going to the right. Now, what about the range, the up and down part? Okay, can we go up or down any? No. What is this graph doing? It's staying fixed at what number? It's stuck at what number? negative 3. So my range would simply be negative 3. And that's it. So it's a function. It has a domain of negative to positive infinity. And it has a range of negative 3. Okay, why is it going to be negative 3? Because we're looking at the up and down part, right? And does this go up here at all? No, if I follow the graph, what is it doing? It's staying here at negative 3. Okay, it doesn't go up or down any. And that's where it's at on the y-axis. This is also called a constant function. Okay, it's constant at negative 3. So it's always stuck at negative 3. Does that make sense now? So if it would have been up here at like 10, it would have a range of what? Range of 10, right? Okay, because it's a constant value at that negative 3. Horizontal lines are also called constant functions. Let's talk about a circle or an ellipse. And this might be an ellipse, and that's okay. Okay, let's say we've got a positive 3 and a negative 3. This is actually going to be an ellipse. Is this a function? Yes or no? No. Why is this one not going to be a function? It's not a function, right? Because if I draw a vertical line here, what happens to this vertical line? It touches twice. So if it touches the graph at more than one place, this is not a function. Now the domain is going to be the values of x. So where does this graph exist from? Well, it never goes past this 2, and it never goes past the negative 4 on the x part, does it? So my domain would be negative 4 to positive 2. What about the range? Okay, the range is a little bit different. And where does the range go from? Negative 3. It's as far as it goes down. And what's the highest value it ever goes to? Positive 3. So your range would be negative 3 to positive 3, right? Because that's your up and down component. Now there's other things that we can do with these graphs, and we can talk about where they increase, they decrease, or they remain constant. So there's 3 things that can happen with these. We're going to talk about increasing, decreasing, and constant functions. So when I'm talking about increasing, that means we go up from left to right. When we talk about where it decreases from, it's going down from left to right. And what about a constant function? Constant functions stays the same. From left to right. So we're going to be talking about the increasing, decreasing, and constant parts of a function. Now here's where students sometimes make a mistake. When we label these, they have to be labeled on the x-axis, not the y. The x-axis. Okay, so increase means you go up, decrease means you go down from left to right, constant means you stay the same. I'm going to give you a graph. We'll actually do probably 2 or 3 of these. because they're pretty simple. I'm going to give you a graph, and you're going to tell me where this increases, decreases, or where it remains constant. So we look from left to right. And if it's going up, that's an increase. Down, that's a decrease. Stays the same, that's constant. Okay, so here is our graph. Now, we need to figure out where it increases, where it decreases if it does it all, and where it stays constant. Now, I look from left to right, so I start here. And I'm going to use arrows to represent what's happening. As I look here, as I follow this graph, it's going up. So that's your increase part. Okay, then it stays constant here, so that's the constant part. And then here it goes down, so that's the decrease part, right? Looking from left to right. So let's now label our increase part. We have to label off the x-axis, not the y-axis. So where is it increasing from? It's increasing from negative infinity. It's going up here on the x-axis. And where does it stop? Increasing. I didn't even label the y-axis because I don't want you to get it mixed up. Have to label off the x-axis. So where does it stop increasing? 4. Negative 4 there. Okay, so that's where it increases from. Now, where does it remain constant? Yep, it stays constant from negative 4 to 2. And where does it decrease from? It decreases, here's the decrease part, it decreases from 2 to what? It's going down, it's going to the right, so it's from 2 to positive infinity. So that's where it increases, stays constant, and it decreases. Let's do another one. Okay, so what's happening on this one? Where do we start? We have to start at the bottom and work from left to right. So you have to work from left to right. Just like we read, okay, we work these out the same way. It's going up, constant, up. So that's an increase here, constant, and another increase, right? Does this function ever go down? Does it ever decrease at all? No, right? Does that mean it would turn back on itself? It does not. When we link these pieces together, just like we did with intervals before, we use a U for union. So if there's two separate increasing parts, we splice them together with a U for union. So let's look at the increase part. Okay, where does it increase from? Remember, we're labeling on the x-axis. Okay, so it's increasing from negative infinity. Stops at what? 0. Then it starts increasing again at what? 3. And it keeps increasing from there. What about the constant part? Where is it constant from? Can someone tell me? Right in this region right here. And that's going to be 0, 2, 3. And what about the decrease part? Is there any decrease at all? Nope, so there is none. It never decreases. Okay. Are we all right with these? Do we see how these are working? Now we're going to talk about equations. And we're going to see how equations, see if they're functions or not. And an equation is a function if you can solve it for y. No, y squared, y to the 4th. Okay. No y's in the denominator of fraction, which we don't really have to worry about those. No y's underneath the root. None of these. Okay, so none of these. Okay, it has to be y by itself, not y squared, not y cubed. Well, y cubed would work, but not y to the 4th or the squared y. Can't be any of those. Now, these are very, very simple to do. All you have to do is see if it can be or is already solved for y. So let's look at this one. I'm not going to have you find the domain and range. You're just going to tell me if this is a function. We're not going to find the domain and range. We'll do that graphically later on. But would this be a function? Yes or no? Okay, yeah, it would be a function, right? Why would it be a function? Can I solve it for y? Yep, move that 5x over. We now have y equals a minus 5x plus 7. And so it's been solved for y, so this would be a function. What about this one? Would this one be a function? Yes or no? It would be, wouldn't it? Right? Why? Because can I move that x cubed over? Yep, you can. You got y by itself. And so it has been solved for y, so this is a function. All you have to do is solve it for y. What about this one? Would this one be a function, yes or no? You think this would be a function, yes or no? No, why not? Okay, this is not a function because of the square there. All you have to look at is the y part. Okay, it is not a function because of the square on the y. Do you think this one would be a function? I think it would be. Why would this next one here, why would this one be a function? Well, I can solve it for y, right? I can divide both sides by x, and as long as you can get the y by itself, then yes, it is a function. So all you have to be able to do is solve it for y. That's it. Don't try to overcomplicate it. If you can get y by itself, it's a function. And you don't even really have to do that. I can look at this and I can tell you that this is not a function. Why not? Because you've got a power on that y. If you've got a y squared or a square root of y or anything like that, it is not a function. The last part of this section is, we'll do two more of these. Well, we'll just do one more, just to make sure we have it completely understood. Let's do one more of these, just to make sure we have it down. Would this be a function or not? No. Why is this one, again, not a function? It's not a function because it has that y to the fourth in it. Right? You don't care about the x at all. All you look at is the y. If it's just y by itself, it is a function. If you have y to some power, like y squared, or y to the fourth, or the square root of y, then it is not a function. Now, the last part of this section, we're going to talk about function notation. And function notation is this, f of x. Okay, this is called function notation. And it can replace y. So a lot of times we can replace y with a function notation, and this is said f of x. Okay, so this is read f of x. And we can use function notation to replace y because a lot of times this might be more convenient to use. So f of x or g of x or any other function of x can replace the y. It just makes it sometimes easier to work with. So we're going to do two of these. And what we're going to be doing is we're going to be solving for y, and we're going to be replacing y with the function notation f of x. So our directions are going to be solve for y and replace y with f of x. So let's start off with this. Okay, we'll just do two of these. So all I want you to do, and don't try to overcomplicate this one either, is I want you to solve it for y. So that just means I get the y by itself on the left-hand side. And once I've solved it for y, then I'm going to replace that y with the function notation f of x. So we're going to replace y with f of x. And you're probably already familiar with this because solving these is something you've done before. When you graphed lines, you had to solve them for y. Same concept here. Solve this for y. So move that 3x over. Minus 3x plus 14. Okay, we're going to solve it for y. And then divide by your negative 7. And this gets it in what's called slope-intercept form, which we'll talk about that next week. Okay, when we talk about more in lines. So divide by your negative 7. That gives you y equals now. Negative and negative makes it a positive 3/7 x. And 14 divided by negative 7, well, that's a negative 2. What do we do for our next step? We replace, now to finish this out, we replace y with f of x. So this is going to be your final finished answer here. You replace that y with f of x. Okay. Let's do one more. Same concept. That's it. That's all you have to do. Solve it for y. Replace y with f of x. Same concept again. Solve for y. Replace y with the function notation f of x. So, simple enough. How about we have a minus 3x squared plus y equals 4. Similar to what you have in your homework for one of the questions. Now, what do? Solve it for y. Okay, so simple enough. Move that 3x squared over. And that gives you y equals now 3x squared plus 4. And what do we do to get our final finished answer? We simply replace that y with what? F of x. And there is your answer, now in function notation. So don't try to make these more difficult than what they are. Solve it for y. Replace that y with your f of x. Okay? So don't try to make these more difficult than what they need to be. A lot of times in this section, there's not much to these, and students try to overcomplicate it. And also there's just a lot of different things going on. None of it is difficult concepts, but a lot of different ideas. And so in this section, a lot of these questions, and in this chapter too, are going to be easy. They're not difficult, and don't overcomplicate it. Don't think there's more to it. You just follow the directions, and don't try to make it more difficult. I mean, what is it? Some of these there's not much to do. But a lot of times I see students way overcomplicating questions. So now let's move on to 2.4. And 2.4 is another section that I'm sure you're familiar with. And 2.4 is the slope. The slope of a line. And your slope is defined as your rise over your run. Okay? Rise over run. That's your slope. It's also called m. So anytime you see a lowercase m, that is going to represent your slope. And slope is always the rise over the run. So that means the y goes on the top. The change in the y, change in the x goes down below. Okay? Rise over run. Now let's look at 4 different graphs that have different slopes. I'm not going to have you find the slope. I'm just going to have you tell me if these lines have a positive slope, a negative slope, a 0 slope, or an undefined slope. Okay, rise over run. Let's start with these 2. Okay, what about these lines? Let's look at the first one here. Is my slope going to be positive or negative? Now, positive value means it increases. Negative value, again, means it decreases. So when I look at this line, what is it doing? Going down, so my slope would be what? Negative, right? Negative slopes go down. And what about the other one? It's going up from left to right, so it has a positive slope. Rise over run. What about the last 2? Let's see if we can remember these. See if we can remember which is which. One of these is going to get a 0 slope, and one of these gets a undefined slope. So the first one here, this one, do you think this is going to have a 0 slope or an undefined slope? Which one? Does anyone remember? 0 or undefined? Remember, rise over run. Does this line, does it go up or down at all? No. That means my slope would be 0. Remember that? Now, what about my vertical line? The vertical line doesn't go left or right, which makes it have division by 0. So this one would have a slope that is undefined, right? Remember those? So these are the 4 different outcomes that you can have. A positive slope here, a negative slope, a 0 slope, or an undefined slope. So I just wanted to show you what the different slopes are. Now we're going to learn how to graph a line when you're given a point and a slope. Okay, so let's try to learn how to graph this one. Now, we can graph a line 3 different ways. We can graph a line with 2 points. Okay, and if we have 2 points, we just simply connect them together. Easy enough. We did that in the last section, in 2-1, on Tuesday, right? We connected 2 points together. That made a line. You can graph a line with a point and a slope. And you can also graph a line when you have an equation, which we'll talk about that later on today. But right now, we're going to learn how to graph a line when you're given a point and you're given a slope. So if you've got a point and a slope, the first thing that you do to graph this line is plot your point. So remember to plot your point. This is x, y. So we're going to go over 5 and up 2. Now, my slope is a minus 3 over 4. So that means I've got to go down 3 from that point and over 4. So from my point right here, this is where I'm going to start. I'm going to go down 3 units. So down 1, 2, 3. So we're going to have to go down 3 and over 4. Always go to the right, never to the left. And I make my new dot. Now, where would my new dot be at? Okay, let's make sure we can label it correctly. So we're going to go down 3. So that makes it a minus 1. And we're at 5. We're going to 4 over. So that's going to make it at 9, right? So that's going to be 9 comma negative 1. And I can connect those together now and graph my line. You just plot your point. Use your slope to move from there. So easy enough on that part. Let's do another one. And then we'll look at how to find the slope from 2 points. And then once we have that down, then we'll look at equations. We'll learn how to graph the equations, and that'll finish up this section. So there's not a lot left. So let's do one more. So we're going to graph a line. We're given a point and a slope. So how about 0, 3? And let's say we're giving you a slope of 5. Okay, so how would I graph this line? We don't need to make it more complicated than what it needs to be. What do we do first? The first thing we do is we find our point. So 0, 3. So that's at 0, and that's up 1, 2, 3 units. Now, what is my slope? M. Okay, M is 5, and I'm going to write this as 5 over 1. So, from my point right here, I have to go 5 units up and 1 unit over. So, from my point right here, I've got to go 5 units up and 1 unit over. And that makes my new dot. So, where would my new dot be at? This was at 0, 3. We went up 5 units. So 3, add 5 to it, makes it 8. We're at 0. We went 1 unit over, so that makes it a 1. You don't have to label the ordered pair, but I think it makes it easier. So you went up 5 and over 1. Draw your line. Now next, we're going to learn how to find the slope of a line. And the way we find the slope of a line with 2 points is you use this formula. This is going to be our slope formula. So this is our slope formula. And you probably have seen this before. So this is going to be our slope formula here. y1 minus y2 over x1 minus x2. I'm going to now give you ordered pairs, and you're going to find the slope. So let's say I give you the point 5, negative 4, and minus 3, minus 8. And I want you to find the slope. Now, it's very easy to do, but where students make a mistake is they get the x and the y mixed up. Because the y goes on top, because that's your rise. The run is the x down below. So x1, y1, x2, y2. Okay, so let's go ahead and find our values and plug them in. Your slope m is y1 minus y2 over x1 minus x2, which that is now minus 4, right? Because that's your y. Minus, watch out for double negatives, a minus 8 over 5 minus, watch again, out for double negatives, a negative 3. Okay, so there's your slope. Now we evaluate it down. We know the double negatives again are going to make those now positive, right? And let's see what we get. Minus 4 plus 8. Well, minus 4 plus 8, that leaves you with a 4. And 5 plus 3. 5 plus 3 makes it an 8. We want to reduce this down. So that then reduces down to a slope of 1/2. I'm going to work out a couple of these homework questions that are the applications. I'll leave some of them for you to do. There's several of them. Okay, but I'm going to work out a couple of these for you. I'm going to work out 7, and I'm going to work out 8. So this is out of your homework. And I'm going to leave the rest of them for you to do. And we'll do 7 first. So we're going to look at our homework here. These are applications. All you have to do on these is find the slope. You've got to come up with 2 ordered pairs and work them out. So I'm going to do 7 and 8. You can do 6, which is an easier one, 5, which is a fairly simple one, and 9, which might make you think a little bit. But I will leave 2 of them for you to do, and I'm going to do 2 of them for you. So question 7. A deep sea diving bell is being lowered at a constant rate. After 10 minutes, the bell is at 600 feet. After 50 minutes, the bell is at a rate of 1900 feet. What is the average rate of change of the depth? Okay, round to 1 decimal place. So we're looking at the average rate of change in the depth. Now, time usually goes in the denominator. So if I write this out, what are we doing? We're changing in time. So what do I have? Minutes and feet. So when we talk about the average rate of change, that's my slope. And that's going to be your feet over your time. In this case, seconds. Oh, sorry, minutes, So it's feet over minutes. We have to make sure we label these correctly. So when I look at this, my average rate of change is the slope. Okay, it's feet per minute. Per means divide. So what do we know about the slope? Rise over run. Y goes on the top, X goes down below. Right, because that's your time. Now, what do these look like as ordered pairs? Well, as ordered pairs, it's going to be the minute followed by the feet. Okay, so minute goes first because that's your X part, right, down below. Feet goes second because that's your rise, or the Y part. So when we look at this, what do my ordered pairs look like? It's being lowered at a constant rate. After 10 minutes, it's at a depth of 600 feet. After 50 minutes, it's at a depth of 1900 feet. Okay, so does everyone see where I got my ordered pairs from? And they're already in the same order that we want. Now we've got our ordered pairs. Nothing really to do but find our slope. And what's our slope formula? M equals y1 minus y2 over x1 minus x2. And that is now going to be x1, y1, x2, y2. That is going to now be 600 minus 1900 over 10 minus 50. And we can work this out. And we can come up with our slope. And it says round it to 1 decimal place. So we're going to take this out to 1 place. So we've got 600 minus 1900. That should make it a minus 1300. And 10 minus 50 is 40. Divide those out. And that gives me now, and that should be a negative down below, negative and negative makes it a positive 32.5, and that's going to be feet per minute. So what does that tell me? That just tells me that we are going down 32.5 feet every minute. So that's all you have to do is figure out where the ordered pairs are, plug them in, find your slope. again, a lot of this should be reviewed. Question 8, same thing. A faucet is going to be used to add water to a large bottle. After it has been filling for 5 seconds, the water on the gauge indicates 15 ounces. After it's been filling for 12, it indicates 29 ounces. Find and interpret the average rate of change in volume of water per second. So we want volume over the second. So that is your y. That is your x. So ordered pairs, they're going to look like second, comma, volume. And we can fill them in. So what do we have? They should be already in the correct order. 5 seconds. 15. We've got 12 seconds. 29. So x1, y1, x2, y2. And my slope is going to be 15 minus 29 over 5 minus 12, right? Watch your values here. Make sure you put them in the correct order. And 15 minus that 29, that's a minus 14. And 5 minus the 12, that's a minus 7. And that comes out to be 2. And what's happening here? 2 ounces per second. So all you need to do to interpret it is just label it. So every second, what's happening? Okay, every second, you are increasing the volume of that container by 2 ounces. It's positive, so it's going up. We do have a little bit more to cover, and we're going to quickly remember how to graph lines. Okay, so it won't take long to finish up this section. So we're going to find the slope and graph, and we need to remember our slope-intercept form. The slope-intercept form is y equals mx plus b. Right, remember that? That is your slope-intercept form. Y equals mx plus b. Your y-intercept is 0, comma b. And the m, well, that represents the slope. So we're going to do a couple of these. And then that'll be it. So we'll probably do 2, maybe 3 if we have time of these. And what I want you to do on these is find the slope, graph, and also get the domain and range. So I want you to find the slope, I want you to graph it, and also give me the domain and range. Now, not very difficult. We want to solve it for y, right? Because that's going to get me my slope, and that's also going to get me my y-intercept. So we need to solve this for y, so we're going to move that 4x over. And now we've got 2y equals a minus 4x plus 8. We'll divide by our 2. And now we've got it in slope-intercept form, which is y equals a minus 2x plus 4. So my slope is a negative 2, and my y-intercept is 0, -4. Oh, sorry, +4. My mistake there. Actually, that's positive. Okay, so we got our slope. We've got our y-intercept. Now, how do we graph it? We've graphed these before, right? We did them earlier. You plot your point, which is 0, 4. Or sorry, 0, 4, so up 4. And this is your y-intercept here. My slope is a -2/1. So I'm going to go down 2 units and over 1 unit. And you can make that second dot. You can label it if you want to. You don't necessarily have to again, but you're going to go down 2 over 1. Okay, and so that would be at the point 1, comma, if you went down 2, 1, 2. If you wanted to label that point. Your line looks like that. And what would the domain and range be? Does anyone remember? Well, the domain would be negative to positive infinity, right? And range is going to be the same what? Same thing. And I know you've done these in previous courses. Solve it for y. Find your slope, your y-intercept, plot your y-intercept, find your second point, connect them together. Let's do one more. And I'll go ahead and pass out the sign-in sheet while we work out this last one. Actually, we may do two. I may talk about a constant function as well. The sign-in sheet here. Okay. How would we find the slope? Graph it and get the domain and range. So first off, has it been solved for y? Yes. Okay. Now, there's no number on the end. So what's my y-intercept going to be? As an ordered pair, there's no number on the end, so it's at what? 0, 0, right? The origin. And that -6, well, that represents my slope. So, how would you graph this line? Where would you start at? 0, 0. And my slope is -6 over 1. So we go down 6 units and over 1. 6, so down 6 over 1. And that makes my second point right here at 1, comma, -6. And when I connect them together, we have our line. What would the domain and range be? Okay. Negative to positive infinity for both. Okay. And we've got one more quick one to cover. Won't take more than about a minute. We're going to talk about a constant function. Okay, this is called a constant function. Now, why it's called a constant function is you'll notice that there's no x on this, right? So it's a constant function. And what that means is that means it stays at 4. So if I were to graph this one, there's really nothing to do. This is a constant function. It's stuck at 4. So since f of x equals 4, or y equals 4, same thing, That would make this a constant function, and it would look like that. It's a constant function. So if there is no x, it makes it a constant function, and my slope would be 0, because horizontal lines have a slope of 0. What about my domain and range? Can anyone tell me what the domain would be? Anyone want to take a guess as to what the domain would be? Yep, it's going to be negative to positive infinity, right? But what about the range? 4. Yep. Okay. What's going to be our homework? Well, our homework is going to be 2.3. You can do them all again. And 2.4. You can do them all. They should not take that long to do this homework. Chapter 2 is much, much quicker to go through. So please make sure that you sign that sign-in sheet. And some of you may not have picked up your homework from last time. If you haven't picked up your homework from last time, I'll put it out so you can pick it up. A lot of you have, but if you haven't picked up your homework,